Hello, welcome to CSC7013 Advanced Math for Computer Scientists. This is Brady Chen. Today, we're going to talk about Module 7, Finite Automata. The theory of automata is a theoretical branch of computer science and mathematics. It is the study of abstract machines and the computation problems that can be solved using these machines. The abstract machine is called the automata. Now here are the learning objectives. We'll first talk about the theory of automata, also known as theory of computation. And then we're going to define a finite automaton. So then we're going to talk about some examples of deterministical finite automata. Automata theory is a theoretical branch of computer science and mathematics. It is the study of abstract machines and the computation problems that can be solved using these machines. Okay, so the abstract machine is called the automata. Okay, now the main motivation behind developing automata theory was to develop methods to describe and analyze the dynamic behavior of the discrete math. Now, these automaton consists of states and the transition. They consist of two things: state and the transitions. Now, normally we use circle to represent a state, and then another circle to represent another state, and another circle. Now, the transition is represented by arrows between circles. Under certain condition, one state, we can state A, can be actually, transferred to another state under certain condition. That's the automaton. So automata is the kind of machine which takes some string as input. Okay, and this input goes through a finite number of states. Okay, goes through finite number of states, and may enter in the final state. Then it terminates at the final state. And we're going to talk about this, in the next couple of slides. Let's first build the models for the automata. Okay, so first we're going to talk about the terminologies used in the automata. So we have three terminologies: symbol, alphabets, and a string. Symbol is just it's the smallest building block. It could be any letter or any symbols like the factorial, pound sign. So this could be a symbol. Here are the examples. A, B, C, 0, 1, any number, or question mark, and a factorial. These are all symbols. Now, alphabets are set of symbols. These are sets. Okay. However, these sets are always finite. So for example, we have, the alphabet, which consists of two symbols, 0 and 1. Or we can have 4 symbols, 0, 1, 2, 3, or another 4 symbol set, which are A, B, C, and D. Now, alphabets are typically use Greek letter sigma, to represent. Now, the number of symbols in alphabet sigma is denoted by sigma, and we use 2 bars around. We know that the number of symbols in a set is called the cardinality of the set. So it is the cardinality of the sigma. Okay. Now, string is a finite sequence of symbols. So once you define the symbol and define the alphabet, which is a set of symbols, and then we can use the symbols in the set to create a string. Okay. So that string is a finite sequence of symbols from some alphabet, and the string is generally denoted as W. Okay. And the length of string typically use this notation. It's the same as the number of symbols. We put the 2 bars on both sides. Okay. Now, for example, we can use W to represent a string 10010. Okay. So these strings are created by the symbols from the alphabet 0 and 1. Okay. So what is the length of this string? W. 1, 2, 3, 4, 5, right? So it contains 5 symbols. So the length of the string is 5. Okay. A string which contains no symbol is called empty string, and typically we use also epsilon. We use that one to represent the empty symbol. Here are some more terms used in the automata. Okay. Now, sigma star. Okay. Remember, sigma is a set of symbols. Okay. It's alphabet. So now sigma star is a set of all possible strings over the alphabet. So now, for example, if the sigma equals the set which contains A and B, so it's a set of 2 symbols, A and B. And then what is a sigma star? Sigma star contains, of course, it's a possible strings over the alphabet. So A is the element of sigma star, B is, and then you use the A twice, and then combination of A and B and B and A, and B and B, A, so A, B. So it's all the possible strings over the alphabet. So you can repeat the A as many times as you want, and then repeat the B as many times as you want, or repeat the combinations of A and B. Okay. So even though sigma, the alphabet sigma, is a finite set, however, sigma star is an infinite set, because it can be actually, you can continue to actually build as many symbols as you want. So the string could be of any size. So another example is like if you have a sigma which contains only one element A. Now what is a sigma star? Sigma star, of course, it should contain epsilon, which is the empty string. Okay, always include the empty string in the sigma star. And then you have A, and A, and A. So you can continue to build this. Okay, so that's sigma star. Now the other terminology we're going to use in the automata is called language. So a language is a set of strings. okay, chosen from some sigma stars. Okay, so language is a subset of sigma star, right? It's just selected the strings from the sigma star. Okay, the language could be finite or could be infinity, depend on um, how many combinations we want to use in the string. Okay. Now the last term we're going to use is called powers of sigma. You know, we use the notation we're going to use is sigma to the n. That's the power n. You know, it's sigma n is the set of all strings over sigma of length n. Okay, sigma star is actually all the possible strings. It could be of any length, but sigma to the n, the power of sigma, it's a set of all strings over sigma of length n. So sigma n is finite. Okay, so let's say, suppose if the sigma is, let's say a and b. Now what is the sigma? Let's say if n is 2 or 3, let's say m is 3, let's say sigma 3, right? So that means it's a set of all strings over sigma of length 3. Okay, so what is this? So we have a, right? So that's a string of length 3. A, B, right? Because you have two symbols. A, B, A, or let's actually follow the order A, B, A, and A, B, B. And the B, A, B, A, B, 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 A, B, B, B. I think that's pretty much all the combination of A and B with length 3. So how many items we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so sigma 3 contains 8 symbols. No, I'm sorry, not 8 symbols. Contains 8 elements. Now each element is a string of length 3. So, okay, here are some examples. Let L be a language which consists of all strings of length 2 generated over the alphabet sigma, which contains 2 elements, A and B. Remember, language could be a subset of sigma star, any subset of sigma star. Of course, the strings of length 2 is a subset of sigma star. Then we know that we can generate the L that way, create a string of 2 elements, So AA, AB, BA, and BB. That's all the combination of A and B of length 2. So from here, we can see that the number of strings equals 4. That's not an accident, because if L sigma is sigma contains 2 elements, and the language consists of all the strings of length 2, so then we will find out that the number of strings in the language L is sigma to the 2, so which is 4. Sigma, that's 2. Now, here are some other examples of languages. So let's say the language of all strings over the sigma, which is also contains A and B, which contains AB as a subword. Now this is different from the previous example. So now, which string contains AB as a subword? Let's see. We used L again. Also, we used L, right? So, of course, AB itself contains the subword AB, right? And then we can say A, AB. Is that right? And B, AB. So each string contains the subword AB. And then A, AB. A, B, AB. Well, it contains the AB twice, but that's fine. You just say in a string that contains the subword AB. BA, AB, right? It contains AB. And BB, AB. Or you can say AB, A, which contains A, and AB, B, which contains AB as a subword. So you can create any string A, B, 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 A, as you know, A, as far as it contains AB. So how many elements contained in the language? It's clear that this language contains infinite number of strings, right? Because you can always create a string which contains AB. As far as it contains AB, then that's part of the language. Okay, so that's the second example. Okay. Here, I'm not going to spend much time on this, but I gave you some time to work on this. So let's create a language which contains all strings over sigma. Now the sigma contains two actually alphabet, 0 and 1. That ends with 0. So you can create a string of binary numbers 0 and 1. It doesn't matter what the string is, but that string must end with 0. Okay. Think about this. Again, think about the number of strings in that language, right? Okay. Let's stop over here. Now let's actually talk about two properties of the automata. Okay. So the first proposition 1, says for alphabet sigma, which contains two elements, A and B. Now with length n, the number of strings can be generated is 2 to the n. Okay, so that's one. The proposition 2, the number of strings of length n, possibly over sigma, is the number of elements in the sigma to the n. Now, let's actually take a look at some examples to illustrate this. Now, the first one, because the number, sigma contains two elements. Okay. Now, if you want to generate the strings of length, say length 2, we know that from the previous slide that the total number of elements could be generated is 4, right? So if n equals 2, then with two elements a and b, you can generate AA, AB, BA, and a BB, right? Now what about n equals 3? Now you can generate a string of length 3. So that's the combination of 3 AA, that's 1, right? AAB, that's the second one. ABA, ABB, and the BAA, you try all the possible actually string of length 3 using A and B. Okay. Then BAB, that's the next one. BBA and the BBB. How many of them? 1, 2, 3, 4, 5, 6, 7, 8. So this is more like a combinatorics problem in math. So you have certain number of elements, and you want to actually generate the combination of these elements of length 3 or length 4, you know. So now in general, let's talk about n, right? So for n equals 2, you know that the sigma contains 2 elements. So the cardinality for sigma is 2, right? So then the language we can generate with n equals 2 is 2 square, which is 4. Now here, next one, n equals 3, sigma is still 2, and the language we can generate is 2 to the 3, 8. So then we can assume that for general n, the number of strings can be generated is 2 to the n. Okay, so if we have if we want to generate a string of length 10, then it's going to be 2 to the 10, which is, I think it's 1024 elements. So it could be A 10 A's and A B, a 9A and a 1B. So you can actually create all the combinations of A and B of length 10. So now proposition 2 is slightly different. Now in that case, you know, if let's say sigma contains 3 elements, A, B, and a C. Now we want to generate a language of length, for example, length 2. Okay, so then you can say, okay, for 3 elements, if we want to generate a strings of length 2, now how many strings we can generate? Okay, now based on this proposition, we know that it's going to be sigma to the n. Now sigma contains 3 actually alphabets, so we can say it's a 3 to the 2, that's 9, 3 square. Now let's see how can we generate these 9 strings. Okay, it's a length 2, right? So let's say AA, right? Okay, so we can actually generate this with certain order. So we first actually create the A, okay? Then first the AA, and then AB, right? A and B, and then AC, right? So then we put the B first, B, then BA, BB, BC, right? And then CA, CB, and the CC. So we have total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 3 to the 2, that's 9. It's 3 square. So now, with all the terminations and the definitions, such as the languages, and we are ready to define a finite automata, or we use FA. Finite automata, or sometimes we call the finite state machine, is a simple idealized machine used to recognize patterns within input taken from some character set, which we use alphabet or sigma. Now the job of the FA, the finite automata, is to accept or reject an input depending on whether the pattern defined by the FA occurs in the input. Now let's take it another way. Think about a language. Remember the language we define, right? For example, if we have an alphabet sigma, so say sigma contains two elements, 0 and 1. And then we define a language which meets certain criteria. For example, one example is the language contains all the strings from sigma of length 2, all the strings of length 2 from sigma. Or the language can be defined as all the strings which contains 0 at the end, right? That's another example we just talked about. So a language is certain, string, could be infinity or could be finite. So now the purpose for the finite automata is to, check if someone gave you a string, say 011101. Okay, now this can be served as an input, okay, to the finite automata. Okay, so this is an input. Now we need to build a finite automata to check whether that string satisfies the criteria, or whether that string is part of the language L. So then we end up that the finite automata eventually going to end up with the conclusion, say, well, we accept that string, or we reject that string. If the string is actually part of the language, then we accept the string. If the string does not meet the criteria for the language and it's not part of the language, then we reject. That's the purpose for finite automata. So finite automata is an abstract machine which have 5 elements. We're going to define these 5 elements, or 5 tuple. Okay, it's the same thing. Now it has a set of states. Okay, we're going to define in the finite automata a set of states and the rules for moving from one state to another. Okay, and then depend on the applied import symbol, we're going to the finite automata going to based on these states and the rule, we eventually say we accept the import, we reject the import. So it's basically an abstract model of digital computer, right? Now think about a computer language like Java or Python. Now the language has to meet certain criteria, right? Like L, we say define L, which is Java. Of course, these language like Python, Java is more complicated than the language we talk about here. So the criteria is much simpler here than Java or Python. However, the concept is the same. And then when people actually write statements, and then we can check that statements meet the criteria of the language. So think about this is like a compiler, right? So the compiler is going to accept this import, and then it's going to actually accept these import or generate an error message to say, no, that's not the Python language, does not meet the criteria, uh, does not meet the syntax for the Python. It's just like this concept. Okay. So now let's define a finite automata. So a finite automata consists of the following 5 elements we called 5 tuple. Okay. The first element is the set of states. And this set of states must be finite. Okay. And then the second one is a set of input symbols. For example, you can say, 0, 1, or A, B, C. Okay, it's a set of input symbols. And then Q0 is the initial state. The finite automata must start from the initial state. And then you're going to move to the next state based on certain condition. Now, which next state you're going to move to is based on the criteria we set up in the finite automata. And then F is a set of final states. Remember, the finite automata are going to actually accept a string, and then this is the input, and then we're going to start from the first state, initial state, Q0, and then based on the element in the input, we're going to decide which is the next state we're going to move to. Okay, and then what's the next state we're going to move to, and eventually we're going to end up a final state. Okay, that final state could be something called accepting state. That means we accept the string because that string reached that state. That's acceptable. Now, the final state could be a rejecting state. So that means you reach that state. So that means this input is rejected. Now, most of the finite state machine or finite automata may have more than one final state. Okay, so F basically represents the set of final states. Now delta, it's called a transition function. Okay, it basically defines, from based on the input at each state. Now, what's the criteria? We define the criteria, so that means based on the input, which next state we're gonna move to. Okay, that defines that's called the transition function. Now, let's actually move to the next slide. So we're gonna actually use a lot of examples to illustrate this concept. So let's discuss the components for the finite automata. Okay, the first one is the input, right? A finite automata must have an input. The input is a string fed to the machine, which the machine will determine whether it is part of the language that the machine was designed for. Remember, the string could be, 0101. Okay, so the purpose for the finite automata is to determine whether this string satisfies the criteria, so it's part of the language we define, right? So the string must only be made up of symbols from the machine's alphabet. That's one of the 5 tuples we talk about in the definition of finite automata, right? Normally we use sigma to represent this alphabet. Okay. Now the string must contain only the symbols from the sigma. So for example, sigma contains 0, 1. So then the string must be a sequence of 0 or 1. Okay. Now the second component is called return. Once the input is fed to the finite automata, And the finite automata can actually move from one state to the other and eventually reach the final state. Now, if the final state is accepting the import, then you're going to return accept, right? Or you're going to actually reject. So the results of running the machine on given import, that's called a return. So initially, this will either be accepted or rejected. So if the finite automata eventually, move from one state to the others and eventually landed in the final state, which is accepting state, then the import is accepted. If reached the rejecting state, then it's rejected. Now that's a return. Okay. The other component is a state, right? State is a resting place while the machine reads more import. So once the import is actually fed to the finite automata, the finite automata going to read each of the import symbol. Okay. Now it based on the current import symbols and the current state. Then it will select the next state. Okay, so the status is a resting place while the machine reads more import. Now, if more import is available, so it just reads one import, and that's the last import. It's the last symbol in the import. Now here is the start state. Again, it's one of the 5 elements or 5 tuple. Q0, right? If you check the previous slide, it's Q0. Now, for programmers, this is known as the program entry point. If you start a Python or Java, you always start the entry point. Normally, the entry point is in the main program. It's the first statement in the main program, right? In Java, it could be in the main, M-A-I-N. Okay, so it's the state that the machine naturally starts in before it reads more import. Okay, so that's start state. Now, the other component is called accepting state. Okay. Now, accepting state is the final state. Okay, it contains a set of states which the machine may halt in, provided that it has no import left. So if you machine start the finite automata accept the import, which consists of sequence of symbols, right? It read the first symbol and combined with the initial start state, it just reaches the next state. Okay, and then it just read the second symbol combined with the current state it is resting in, right, and determine the next state. So then the finite state machine keep reading the symbols in the import until it reaches the end of the import stream. Okay. So accepting state basically means, so when the finite state moves from one state to the other, it eventually reaches the accepting state, which is good. That means the import is part of a language, and we accepted the import, right? Now, another state is called a rejecting state. So it's any state in the machine which is not denoted as the accepting state. So that means the string is only rejected if the machine halts in a rejecting state with no more import left. So we reach the end of the import, but sorry, you are actually eventually landed in the rejecting state. So we reject that import. Okay. So this is basically what the finite automata, does. Accept the import based on the rule. Decide whether this import is accepted or rejected. Now, the dead state, it's a kind of state, but sometimes it's called a trap state. It's a rejecting state that is essentially a dead end. So that means if we have an import, right? The import could be a string of symbols. Now the import goes into the finite automata, and with the start state, let's say A is a start state. And then you basically read the first import. Okay, the first import is 0. Okay, so let's say, okay, it's a 0, and then we're going to move to another state B. Now the next state is 1. Based on the rule, we're going to move to another state C. And that next one is 0, then we move to D. Okay. Now next state is 1 again. The import is 1 again. And then based on the 1 combined with the current state D, we're going to decide which is the next state. Okay. The next state could be another state, which is not A, B, and C, but it could be, the previous already used state. Okay. If next one's 1, then we have to move back to B. And then the next one's 1 again. So based on rule, if it's 1, then we go to C, right? And then if the next one's 1, then now the current state is C. Now we haven't defined that yet, but it could be another one. Say if the current state is C, but the import is 1, like we actually mentioned here, then you go to E. So we can just keep going until we reach the last state, which is, say, F. Okay. Now, when we reach a state F, it's a dead state. For example, if we reach the end, it's a dead state. However, now we reach a rejecting state. Rejecting state is not necessarily a dead state. It's just that we reach that state and we have no more import, right? Okay. So if for another state, it could be, if we have another import, which is longer, then it could be actually, we can be actually out of the rejecting state. So if you reach the rejecting state, and then we only say this import is rejected. But doesn't necessarily mean every string. If we actually at the middle of somewhere we reach the rejecting state, and if we have more import symbol, then there's a way we can be out of the rejecting state, and we will back to normal, and we eventually end with the accepting state. Now the dead state is different. If you somehow reach G, a dead state. Now, if we have 0, 1, 0, and then for dead state, then there's no way to be out of dead state. Okay, so which means for the rejecting state, it could be like, okay, if the next import value is 1, then we'll be back to the previous state. Okay. Okay, if it's 0, we can be all the way to B. Okay, so there's a chance that from B we can still actually move forward to the accepting state. But for the dead state, that means, okay, if the next import value is 1, then we end up in the same state. If next import is 0, we also end up with the same state. So we're trapped. So Once we reach the G, no matter what's the follow-up symbols in the import, we will never be able to get out of G. So that G is the dead state. Okay, so we're going to check this with more examples. And the other component is called transition. It's a way for a machine to go from one state to another given a symbol from the import. So transition is defined as just like a function. So transition delta is defined saying what's the current state and what's the current import symbol. By the combination of current state and import symbol, and we define what's the next state we're going to go. That's basically defined as like a function. So transition may even point back to the same state that they have come from. Okay. Now in this case, we call it a loop. Like in this case, we move here. Let me actually use different colors so you can see it clearly. So if we reach that point, okay, then we move next, and then we move next, and then based on the value which is 1, right? And also the current state. The current state is F. The value is import symbol is 1. Then we're going to move back to B, right? So that means the state F combined with the import symbol, then we will go back to the state B. So it can actually move back. And that's called the loop. Okay. So we know by definition, finite automata has 5 tuple, 5 elements. Q, okay, which is a set of states and a set of symbol, initial state, and a set of final state, and the transition delta, right? These are 5 elements. Now, FA is characterized into 2 types. There are 2 types of FA, the finite automata. One is called deterministical finite automata. Now the other one is called non-deterministic finite automata. And for deterministic of finite automata, we use DFA, and the other one is NFA. Now we will actually talk about both of these 2 types. Okay, let's move forward. Let's talk about deterministical finite automata, DFA. Now by definition, a DFA is 5 tuple, Q, sigma, Q0, T, and I'm sorry, it's F and the delta. Okay, so Q is the finite set of n states. That's the same as general definition for the finite automata. Actually, the first 4 tuples, first 4 elements are basically the same, as the general finite automata. Now, the only difference between deterministic finite automata and non-deterministic finite automata, NFA, is the transition function, the last element. Okay, the first 4 are basically the same. Now, sigma is the alphabet of import symbol, and the Q is the special start state. Of course, Q0 is the start state, which belongs to the general finite set of Q. So it's a subset of, it belongs to the set of states. F is a set of accepting states, okay, or final states. Again, F is a subset of Q. So now here's the definition for delta, the transition function. So for deterministic finite automata, delta is a transition function that maps the state, a state and a symbol to state. So that means if we have a finite automata, say, let's say, this is a finite automata. Okay. Now this is the start state. Okay, we start from here. Here's intermediate state, and the D is we call the final state. So now here's the transition function. The transition function basically says, now given the state, let's say state A, now combine the current symbol, okay, current symbol, for example 0, and then we will map to B. So that means if the current symbol is 0, we're going to map to B. Now if the current state is A, but the current state symbol is 1, we're going to map to C. Okay. And then we have to define the delta for each state, right? So for example, if delta B, if the delta, B, if the current is 0, we're going to map to D. Now if the current state is 1, if it's 0, current state is 0, we map to D, right? That's basically what it says. Now, if the current state is 1, we map to what? We haven't defined that yet. Now, there's a couple of different possibilities. If the current state is 1, the current state is B, and the value, the symbol is 1, then we could map to D as well, right? In this case, we're going to say, okay, for 1, 0, and 1, we both map to D. Okay, that's okay. That could be the case. But it could be something else, saying if the current state is 1, we're going to map to C. Okay. We can do anything we want, right? So then, now we're going to define the delta for, like, if its current state is C, if it's 0, we're going to map to D. If the current state is C, if the value, the symbol is 1, we map to D as well. So then, both 1, 0, and 1, we map to D. Okay. Now, for D, then we're going to define the delta for D, right? Let's find some free space. We can write this definition. Let's say I can just squeeze that space. So delta D0 equals what? Delta D1 equals what, right? If delta 0, then we're going to say, okay, if it's 0, we map back to B. If it's 1, we map back to C. So then if it's 0, we map back to B. If it's 1, the current state is D. The current value is 1. We map back to C. Now that's a complete definition of the transition function, right? Then we can decide if given us, input 0, 1, 1, 0, whether this input will be accepted by this finite automata or not, right? Let's just check. So the starting point is A. The first input is 0, so we're gonna actually, move from A because the value is 0, and the starting point is A. So based on the transition function, it's A and a 0, right? A and a 0. So you're gonna move to B, right? Now we check the state which is B, and then the second input is 1, so we have a B and a 1.
B and a 1. So then we can have a B and a 1. So we're going to move to C. Now C, we check the C, and then the import symbol is 1 again, right? Now, so we have a current state C, and the import value is 1. Then we're going to check the C and a 1, which goes to D, right? Okay. Now, the current state is D, and the last value is 0. Okay, the symbol is 0. So we have a D0, right? So the D0, that's the first one, D0, which actually goes all the way, D and the 0, which goes all the way to back to B. Okay. So this finite automata will actually take this import 0, 1, 1, 0, and eventually it will reach B at the very end because there's no more import. Now, if B is not the accepting state, then we're going to reject this one. If B is the accepting state, then we accept it. Now, suppose in this case, D is the accepting state. D is the only accepting state, the final state. Then we will reject this. Okay. So this example is not really clearly written because we have small space, but we will actually take more examples. Now, normally for the transition function, we're going to actually write as delta, that's the function name, and here's the Q, that's the state, and sigma, that's the symbol, right? So Q, that's the Cartesian product. So Q times sigma, that means that the delta going to accept a 2 import value. One is the state, the other one is the symbol. And then you're going to decide what's the next state you're going to go. Okay, so that's the delta. This is actually a kind of math notation. So in the DFA, the Deterministic Finite Automata, for a particular import character, let's say 1, the machine goes to only one state. Okay, so that means if it starts from the current state A and the import character is 1, then the transition function has to define what's the next state to go. So the transition function is defined on every state and every import. So that means if the current state is A, the current actual import is 1, then the transition function delta has to define what is the next state. If it's B, then it's B. Okay. There's no ambiguity here. So, which means in DFA, null or epsilon, that means the empty move is not allowed. Or in another word, DFA cannot change state without any import character. So that means the current state is A, and there's no import, and then it transfers to next state. That's not allowed. Now, later on, when we talk about non-deterministic finite automata, we'll find out, the change could be like a random. Okay. So, here's how we're going to execute our finite automata on the import sequence as follows. So, if for the deterministic finite automata, DFA. So let's start with the start state, right? So if the next import character matches the label on the transition from the current state. So let's say current state is A. Okay, the transition, the label on the transition is 1, goes to B. 0 goes to C. So that's a label. Okay, that's a label. Now if the next import character, okay, So if that's the start state, that means the next input character is the first character, right? Then that's if that character, the input character is 1, okay. From the current state, the label says 1 goes, if the label is 1, it goes to state B, label 0 goes to state C, then the next import matches the label on the transition from the current state to the new state. Okay, now that means this import matches this label, right? This import 1 matches the label 1. So then from the current state A, we go to B. That's defined. Now if the current import is 0, and then it matches the other label 0, then A gonna goes to C. Okay. So to decide which state we will go, it will actually check both the current state and the current import. Okay. Now we continue with this transaction on each import character. So the next character is 0, and next, then we're gonna actually check what the finite, state machine actually defines. What's the next label for state B? Okay. If no move is possible, then stop. And if accepting state, then accept. Okay. Let's actually check. Okay, so let's warm ourselves up again with the terminology. So we say alphabet is the set sigma, right? Which contains all the symbols for the finite automata. Okay, so in this case, sigma is A, B, C, and D. Okay, so these A, B, C, and D are symbols. Now the string could be, if the symbols are A, B, C, and D, the string could be C, A, B, C, A, D. Any combination of these symbols. It's a valid string on the alphabet set. Okay. Now here's another example. 011, 0110 is a valid string on this set sigma equals 01. Okay. We cannot write AB101 out of the set sigma equals 01 because AB are not a valid actual symbol in this sigma. Now the length of string we also define as a number of symbols in the string. Okay. So in this case, S is 0110 and the length of string is 4. Okay. Now if the length is 0, it is called empty string. So we actually use either lambda or epsilon, okay, to represent the empty string. A finite automata can be represented graphically, known as state diagrams. Actually, we already used the state diagram in the previous slides, but let's actually formally define the state diagram. Okay, we use circle with the name inside to represent the state. So typically, in this example, I normally use circle and capital letter to represent the state. If you look at the other textbook, or if you search for any information about the finite automata online, you might see some people use 1, 2, 3, 4 to represent the state. That's okay, but here we always use A, B, and the C, or D, E, F, G, or whatever. So we use the English capital letters to represent the state, and the letters inside the circle, that's the state. Now the arcs labeled with import alphabet show the transaction. So if we define, say, here's the state A, And here's the state B. Okay, two states. And then that's the arc labeled with import alphabet. Supposedly, the alphabet we use is 1, 2, right? If we define the set of symbol, which is 0 and 1. Okay, I'm sorry, it's not a 1, 2, it's 0 and 1. And then, so then the arc labeled with either 0 or then arc labeled with 1. This is actually define the transition. So the transition has two elements. One is the state, okay, and the other one is the label. Label has to be one of the symbol defined in the set of symbols. So the label could be, that's arch label, and coming originally from the state A, and the label 1 originally from the state A. And then, based on the current state A and the label, we actually uniquely define what's the next state, which is B. If it's A combined with 0, that's B. A combined with 1, that's C. Okay, that basically defines the transition function. So the arcs labeled with the import alphabet shows the transition. Okay, the initial state, the start state, is denoted by empty single incoming arch. So normally we use, the incoming arch. It's coming from nowhere. Okay, so there's nothing before the arch. So that means A is the start state. Okay. Now the final state is indicated by double circle. So let's say we define the finite automata. So B combined with 0 goes to D, and B combined with 1 goes back to A. That's okay. That's totally legitimate. And then C combined with 1 goes to D, and C combined with 0 goes to B. And D combined with 1 come back to B. That's okay. And D, if it's 0, goes back to C. That's okay. So that defines the transition for each value of D, and the label, it defines what's the next state. And then if D is the final state, we pretty much actually use the double circles. So that means this is a final state. So now this is a complete finite automata. And actually it's a deterministic finite automata, because for each state and each import value, then the next state is uniquely defined. So that's deterministic finite automata. Now let's define the non-deterministic finite automata, DFA. Oh, I'm sorry, it's a NFA. That's a mistake. I need to correct this. Okay. NFA is similar to DFA. It looks similar, but it's very different. Okay. It's similar to DFA, except the following additional feature. This following additional feature makes a huge difference. Number one, in NFA, null or epsilon move is allowed. So that means in the non-deterministic finite automata, it can move forward without reading symbols. That's interesting. So let's suppose we have a current state A. Now A can move to state B without reading any symbol. So the second one is it can transit to any number of states for a particular input. Okay, so that means if the current state is A, now if the input is 0, then it can move to B, okay, or it can move to C. Or it can even actually move back to A. That's kind of weird, right? So now our current state is A, and the input value is 0, and A combined with 0, then what's the next state? I don't know. I don't know what's the next state, but I can tell you what's the possibility. Which could be the possible next state? So the possible next state could be A, could be B, could be C. That's the reason why we call it non-deterministic finite automata. Okay, it sounds weird, right? But it is a finite state machine. It's a finite automata, and it has its advantage and disadvantage. So these above feature don't add any power to the non-deterministic finite automata. If we compare both in terms of power, both are equivalent. Okay, so due to the above additional feature, NFA has different transition function. Okay, the transition function is different. Everything else is the same. It has the same number of, it has a Q, which is a set of the states, and it has the sigma, which is the alphabet, which is a set of the symbols, and it has a starting state, and it has a final state. But the transition function is different. So instead of like for the DFA, the transition functions uniquely define what's the next state. But in the non-deterministic finite automata, transition function can be written as this. So we have a current state and import character. The import characters could be coming from the set of symbols. Like if sigma is 0 and 1. So it can be, delta could be, from A to 0, from A to 1. And it also can from A to epsilon, which is empty, which is the null actually state. Oh, no, I'm sorry, which is a null symbol, which is empty symbol. There's no symbol. Okay. So that's why it's a sigma times epsilon. It could be, sigma or the epsilon. Now, which potential state the transition function is going to move to is also uncertain. But it might be any of the state. Okay, so potentially it could be 2 to the q. Okay, if we actually use the, two symbols, sigma, it's going to be 2 to the q. The q is the number of states. What does that mean? We're going to talk about this in the next, module. So in this particular module, we are not going to talk about the NFA. We only discuss DFA in this module. Okay, we're only going to focus on the examples of DFA. But in our next module, we're going to focus on the NFA. So let's take a look at an example. Let's build a DFA that accepts strings that contains 0, 1 as a subword. So we want to build a finite automata that accepts strings that contains 0 and 1 as a subword. So that means the finite automata we want to build will accept strings like this: 0, 0, 1, 0, because this import contains 0, 1 as subword. What about the second one? Let's say 0, 1, 1, 1. What do you think? This string should be accepted as well, right? Because it contains 0, 1 as a subword. Now, let's take a look at another string: 1, 1, 1, 0, 0, 0, 0, 0. These two strings, 1, 1, 1, 0, can we find 0, 1 as a subword? No, we can't. And same with this one, 0, 0, 0, 0. There's no 0, 1 as a subword. So we hope that we will build a finite automata to accept this string, and reject that one, right? Let's see how can we build the deterministic finite automata. Let's actually start with the start state A. The start state A will actually has an arrow coming from nowhere. Okay. Now, if the first import character is 0, let's look at the best scenario. Okay. If the import character is 0 and the start state is A, then let's assume we will go to B, state B. You know, the start state A combined with the import character 0, we will actually reach the state B. And state B is a very good state, right? Because with state B, the most recent import was 0. So that means we just need to get 1 next. Then we will get 0, 1, right? So if we get 1 next, start from the state B, then we will reach a state which is accepting state, right? Because 0, 1 contains the subword 0, 1. Now that's the best scenario. So we have 0 and 1, which reaches the accepting state. Now once we got 0, 1 and reached the accepting state, if we actually have any characters after 0, 1, it doesn't matter. It's still accepting state, right? So for example, if we got 0, 1 as two characters, and then it doesn't matter what's the next one. It's a 0 or 1 or 1 or 0. Because the first one 0, 1. So no, it doesn't matter what's the follow-up string. That string should be accepted already, right? Because it contains the 0, 1. So that means once you reached the accepting state, then it doesn't matter what's the follow-up state. If it's 0 or 1, we will still land at accepting state. So we can still actually stays in C. Now that's not the whole picture yet, right? If we start from A, now if our first character is 1, okay? So if it's 1, that means we're not closer to the accepting state, because it doesn't matter what's the next character, whether it's 0 or it's 1, 1, 0, 1, 1, both are not the, accepting, characters. We want 0, 1, not 1, 0, 1, 1. So 1 is not closer to the exception state. So in that case, we're still waiting for 0 first. And then we hope that the character after 0 is 1. So then we reach the accepting state. So in this case, if it's 1, we have actually option. So the first option we can actually stays in A, right? So if the current state is A, the import character is 1. So A and 1 we don't reach B. We still stays in A. Until the next one is 0, then we reach B. If the next one is still A, then we can still stays in A, right? We can still stay in A. So that's one thing. Now, let's see. Suppose I got 0. Initial state is A, but then the character is 0, and we reach B. So we hope the next one is 1, but if the next one is not 1, it's 0. Now, what are we going to go? We can go to another state. It's definitely not the accepting state. We can go to another state, but we can still actually say we stays in B, right? So now we got 0 and another 0. So we 0, 0, we stays in B. And until we got 1, then we go to the accepting state. Now that gave us the complete picture of the finite automata. Now, let's take a look at this and to see what's the first element Q. What's the set of state? Now we have set of state A, B, and C, right? And then what's the set of symbol? It's a 0 and a 1. And what's the initial state? A, right? What's the set of final state? There's only one final state, C. Okay. Now what's the transition function, delta? We can actually check to build the delta. So let's say for delta, if the initial state is A, let's say if the initial state is A, now then we look at the two different import, right? Two different imports. If the import is 0, A combined with 0, what's the next state? B, right? So A combined with 0, we reach B. Now if A combined with 1, A combined with 1, what's the next state? We stays in A, right? So that's the whole story for state A. Now let's look at the B if we are currently in B. Now if B combined with 0, we stays in B, right? If B combines 1, we actually finally reach the accepting state C. Okay. So that's the whole story for B, and let's look at the C. If the current state is C, and if we got 0, and then we still stays in C. And then if it's 1, we stays in C, and the C is accepting state. We use the asterisk to mark the C. So that's the transition function. Let's look at another example. Let's build a DFA for language L1, which is a set of all strings over 0, 1 of length 3. Okay, so that in this case, we want to build a finite automata to accept all the string of length 3 over the alphabet 0 and 1. Okay, so let's start with A. We know that if we actually have an import character 0, then we are going to next state. And if we continue to have import 0, we're going to next state, right? Now we have 2 zeros. And then if we continue got a 0, we're going to a state D. Now 0, 0, 0, that's a string of length 3, right? So it looks like a D is an accepting state, right? Now what about if we start with 1, 0, start from A, state A, and then with the first character is 0, and the second character is 0, and the third character is 1. We're still going to actually go to the accepting state, right? So it doesn't matter whether it's 0 or 1. So whether it's 0, 0, 0, or 0, 0, 1, both of these are the string of length 3. So now let's come down to the diagram. We find out, A will go to B. State A will go to state B for import 0. And for import 1, we also go to B, right? It doesn't really matter whether 0 or 1, because it's only actually what matters is the length. Okay. So starting from A, if the initial import is 1, the next import is 0, the next import is 1, 1, 0, 1, we still go to the accepting state. Okay, so the value, the character doesn't matter, the length matters. However, once we reach D, if we continue to import a character, okay, so let's say 0. So that means we already have accepting state, reached the accepting state. That means we already have 3 characters in the string. But now we want to put the 4th character, which is 0. So now if we add 3 character, add another character which got 4th character. So now the string is of length, not 3, right? It's 4 now, so length 4. Length 4 is not in this language L1. So that means this string is not an accepting string. So that means if we actually continue to, have an import character from state D, we reach another state. Now that state is a rejecting state, so we're not going to accept it. Okay. The same thing with another 1. If we add another 1, it doesn't matter whether we add a 1 or 0, but this is going to make the string of length 4, so it's no longer an acceptor state. So this is a kind of tricky one. So if the length of the string is less than 3, like a B and C, it's not acceptable. Okay, if it's E, it's not acceptable. Only D is accepting state. Now after E, if we have 0, this is going to make the string like 5 characters, which is a string of length 5. So we're going to stay in this E, still actually not acceptable state. So that's actually the dead state actually. This is actually if 1 stays in the state E. So state E is actually a dead state or trap state, right? that's the accepting state, the final state. Now, this is it. That's the finite state machine. That's the deterministic finite automata. So we got the diagram for the finite automata that check whether the import string is acceptable or not. If the import string contains 3 characters, then it's acceptable. You're going to reach the final state, accepting state. If it's less than 3 character or larger than 3 character, it's not acceptable. Now let's check what's the transition function. Okay. So if we just are currently in the initial state A. So if we got in character 0, so we know we're going to reach the next state B, right? And we got a 1, we'll reach the next state B. If we are currently in B, then it doesn't matter what's the character, import character, we're going to reach C. Now, if we're in C, we're going to reach D. We're going to reach D for either 1 or 0. Now, D is acceptable. It's the final state, accepting state. But if we continue to actually, add a character, so D combined with the next import character 0, we're going to reach E. And that also going to reach E. So that's a trap state. If we are currently in E, so it doesn't matter how many which the character we add, we stays in E. So that E is the trap state or dead state. Okay. So the final state is D, right? Example 4.
Let us build a DFA for language L, which is a set of all strings over A, B, C, D, all the way to X, Y, Z. That's the alphabet. That starts a word for, F-O-R. Now, how can we build this finite automata? It sounds scary, right? Because the set the set of symbol contains A, B, C, D, and 26 characters. But we want to build a string that can start with the word for. Okay. Now, how can we do this? Let's say if we have, if we build a word like FOR or forward or forward, these are all accepted, right? Now, any other word like A, FOR or whatever. So now this word does not start with FOR, so it's not accepted. So the concept is very clear. So let's start with A, state A, which is the initial state. So let's start with the easy one. Suppose everything actually goes well. So we start with the initial state A, and the first import character is A, or 4, F. That's good, right? It's actually 2 more steps closer to the word actually 4. So then we reach B. And then if the next import value is 0, oh, I'm sorry, it's not 0, it's O. Then we reach C. And then the next ones are, which is good, right? We reach the accepting state, D. Now, it really doesn't matter what's the state, what's the character we actually enter after D.
right? If it's A or B or C, X, Y, Z, it's all accepted. So it still stays in the accepting state. Now the only thing we need to think about is if the first character is not F, now we reach another state, E. This is not acceptable, right? If the first state is not F, it could be A, could be B, but not F. Then we reach another state. Now, once actually we reach that state E, it really doesn't matter what's the follow-up import value, right? A to Z. They stays in that state, okay? Because any actually string start with non-F, this is already not acceptable state string. So that is actually the trap state, right? Because once we reach E, that means the starting character is not F. Now once we reach B, so the first character is F, that's good. But the second character is not O, then we reach the trap state. Because FA, it doesn't matter what's the follow-up character. We're not going to accept that string. Again, for C, if it's not R, then we reach that state. So this is the finite state machine. This is the finite automata. So we can actually build the transition function delta, right? The delta is going to be pretty big. So if it's A, B, I'm sorry, it's A, B, C, D, E. Now the import value is A, B, C, F, O, R, X, Y, Z. So if A combined with A, the state A combined with lowercase a, we're gonna go to E. A combined with F, we go to B. Everything else goes to E, right? That's gonna be a very big table. And then if we're in the state B, then we have to make sure only when we actually have the import characters O, then we reach C, right? In other case, we're going to actually end up with E. Now, if we are in the state C, then the only acceptable characters are, in this case, we reach the final state D. Otherwise, we're going to actually end up at the trap state E, right? So once we're in D, then we stays in D. Okay, it's all D. Okay, and once you are in E, then you stays in E. Okay. Okay. That's the example 4. Let's look at the next two examples, 5 and 6. So let's build a DFA for the language L, which is a set of a string over 1, 0 or 0, 1 that contains the string 0, 0, 1, 1. And the next one is just the opposite. We build the
the deterministical finite automata for language L, which is a set of string over 0, 1, that does not, they don't, contains the string 0, 0, 1, 1. The first one says which contains the 0, 0, 1, 1. The next one says don't contain 0, 0, 1, 1. Now, let's see how to solve each of the problem, and hopefully we can find an easy way that once we solve the problem 1, the example 5, then we can easily find a solution for example 6. Okay, let's actually do this. Now, first, example 5. We want to build a deterministic finite automata that accept the strings which contains 0, 0, 1, 1, right? Accept the string which contains 0, 0, 1, 1. Okay, so let's build the finite automata. So let's start with the state A. Okay. Now, if the first import character is 0, then we will go to the next state B, because we want to build a finite automata which is accept a string which contains 0, 0, 1, 1. And then if the first one is 0, that means this is good. It's closer to the string we try to build. And if next one 0, that's good, right? We're even closer. And then if the next one is 1, that's good. Next one is, we reach D, and next one is 1, we're good, right? Then we reach the accepting state. So that's the perfect case. Okay. Now what about if the first one is not 0, if it's 1, right? So that means we're not going to be able to build a 0, 0, 1, 1, because if the one starts with 1. So what we're going to do is, okay, that's fine. We can wait until we got 0, right? So if the first import character is 1 when the initial state is A, then we stay with A. We are kind of patient. We just want to, stay with A until we got a 0, right? So once we got a 0, now we reach B, and then if the next one character is 1, so that means we actually start with A, and then we have import value 0, and then at B we got a 1. Now, that's not something we want. We want a string which contains 0, 0, 1, 1, but this one actually got a 0, but next one is 1. So no matter what is the next character, 0 or 1, we're not going to actually be able to build a 0, 0, 1, 1. So in that case, what are we going to do? If we got a 1 at the B, we're going to move back to 0, A, right? So then if we are lucky, we reach state C. So that means we already got 0, 0, right? And then we reach C. Now, if the next one is 1, then we reach D. But if the next one is not a 1, it's another 0, right? What are we going to do? Are we going to actually move all the way back to A? No, because even though we got 3 zeros, then that's still a right direction, right? Because all we need to do is get a 1, 1 for the next 2, right? So we're not going to go all the way back to A. we're probably going to stay in C, right? If we got a 0, we stays in C, because this 0 combined with the previous 0, they're going to make the first two zeros in the subword. Okay, so we stays in C. So now we can go all the way to D if we got a 1. Okay, so once we reach D, what does that mean? So we already have 0, 0, 1. So if we got next one, then we are good. So we actually successfully get a substring, which is 0, 0, 1, 1. But what about if we got a 0? Once we reach D, once we are in the state D, but we got 0 in our next import. So that means we got a 0, 0, 1, 0. That's not good, right? We want to build a 0, 0, 1, 1, but we got 0, 0, 1, 0. So what are you going to do? So we have to actually roll back. And where are we going to go back? Are we going to go all the way back to A? No, because we already have 1, 0 here, right? So all we need to do is we add another 0 and add a 1, 1 so we can build this one. Okay, so we're not going to go all the way back to A, but we're going to actually go all the way back to B, right? So that's about it. So we're complete for state D. So if D, once we reach the state D, if it's 0, we go back to B, and if it's 1, we reach the final state. So that's the deterministic finite automata that accept the string which contains 0, 0, 1, 1. Okay, let me eliminate some of the unnecessary thing so then we can make it better. So let's erase that one. Let me erase this one. Okay. Yeah, just clean up this one. So we actually successfully built a finite automata, deterministic finite automata that accept the string which contains 0, 0, 1, 1. Okay, that's it. I think that's example 4, right? Now let's take a look at the next one. Example 5. I believe example 5, we try to build a deterministic finite automata that accept a string which accept strings which do not contain 0, 0, 1, 1. Now how can we do this? It sounds scary, right? But it's actually not. Since we already built the finite automata that accepted strings which contain 0, 0, 1, 1. Now we want to build the finite automata which accepts a string which don't actually contain 0, 0, 1, 1. Now all we need to do is we just reverse the previous one. What does that mean? Oh, I'm sorry. We missed one more. For state E, we also need to build the transition, right? Once we reach the state E, it's accepting state. So that means if we have any more import values 0 or 1, it still actually ended with accepting state, right? Because we already have 0, 0, 1, 1. So it doesn't matter what's the follow-up import values. Okay, so sorry, I missed that one in the previous example. And now let's look at the next one, right? We try to build a finite automata which accept the strings that don't contain 0, 0, 1, 1. Now, it's pretty simple. We just reverse the previous one. What does that mean? So that means in the previous automata, finite automata, the E is accepting state, right? Now we will make this E non-accepting state, because once we reach E, then we're finished. That means this string contains 0011. Now we want the finite automata that accept strings which don't contain 0011. So once we reach E, it's not acceptable state, not accepting state, right? Now, if we are in D, that's accepting state, right? C, that means we don't contain the 0011. That's accepted state. B is also accepting state. A is also accepting state. Right? Now everything else is the same. One, 0, 0, 1, 1, 0, 0. What else I missed? No, I don't miss anything. Okay, that's good. So that's the deterministic finite automata that accept strings that don't contain 0011. Now once we reach E, it doesn't matter what's the follow-up import values, because we already have 0011, so this is not acceptable, right? So that E becomes a trap state, because once we reach E, then we already have this 0011 subword. So that string is not acceptable, no matter what we have afterwards. Okay, it's a trap state or data state. Okay, so now it's your turn. Example 7. Let us build a DFA for language L, which is a set of all strings over 0, 1 that don't contain the string 0, 1. Oh, I'm sorry, don't contain the string 101. How can we build that finite automata? I'm going to post this on the discussion forum on the Blackboard. So feel free to provide your answer on this. Sorry, feel free to provide your answer on this one.